So let's start with 0.6. So as I mentioned, this is the chapter before chapter 1. This is chapter 06 lesson. Okay, so in this chapter, we're going to be talking about matrices, singular matrix. A matrix is a rectangular array, right? An array is something that has like rows and columns. It's a rectangular array of variables or constants arranged neatly in rows and columns. I think this is why math teachers love matrices, because everything is just in neat rows and columns, right? And they're enclosed in brackets. A matrix is a way of organizing information, and it also not only organizes information, it also makes it possible to perform operations on that information. All right. Now, each value in a matrix is called an element, and this is what a matrix looks like. Now, remember, it's always rows and columns in that order. It's never columns and rows. It's always rows and columns. So when I say this is my matrix, I say, okay, it has 3 rows and 4 columns, never the other way around. Okay? Now, every matrix has a name given to it. Usually that name is a capital letter. So for example, this matrix here is matrix A. Okay, capital letter A. All right, the dimensions of a matrix, basically it's the size of a matrix, but you give it by rows and columns. It's just like you would give the dimensions of a rectangle. You would say it's like 3 by 4. The dimensions of a matrix are basically the number of rows and columns. And we write it as m by n, and that's how we read it, m by n. So for example, this matrix A above has 3 rows and it has 4 columns. So I say this is a 3 by 4 matrix. Okay? All right. So let's take a look at this. This is another matrix A. What are the dimensions of this matrix? It's 4 by 6, right? Never 6 by 4, because that would be, like a different matrix altogether. And they're not interchangeable, all right? This is a 4 by 6, 4 rows, 6 columns. Now, each of the elements inside also has a location, a place, right? So if this matrix is capital A, each of the elements inside gets a little a, and then you give it its position, right? So imagine instead of calling Olivia, imagine if this is F period, right? Imagine I call her F11, and then, you would be like F12, right? And then you would be F21, right? Imagine. So that's pretty much what this is, okay? So when I say A23, this is little a, the element A, in the place 2nd row, 3rd column. So I go down to the 2nd row, over to the 3rd column. That's that 0 over there. So this is 0. Okay? So who is A35? 5. And A46? 11. And A12? Correct. Okay? Yeah.
I'm doing it the other way.
Right. Okay. So this one, this left top, right? That's like the first element. Okay, and then it all starts from there. That would be A11, not 11, 11. Yeah. Okay. So, matrices with special names. If you have a matrix that is just 1 row, conveniently it's called a row matrix. Okay, like this is a row matrix. It has dimensions 1 by 4. Okay, and then a column matrix is one that has 1 column, like this one. This has dimensions 2 by 1. A square matrix has the same number of rows as it has columns. This specific one has what dimensions? 2 by 2. In general, a square matrix is called an n by n matrix, okay? A zero matrix is any matrix of any dimension where every element is just 0. Okay, a zero matrix is similar to the number 0 in many respects in like the number world. Okay, an identity matrix is a square matrix in which every element on the main diagonal is 1. Okay, so what is the main diagonal? So if you have a square matrix, remember how we said this is that initial element? That diagonal, starting from the top left going down, that is the main diagonal. That's like if you are downtown somewhere, that's Main Street. That's where it all happens. Yes.
Is it possible to go from the top right down to
Nope. That's like nothing.
It's always top left.
Second class citizen. Yep.
What is a square matrix with all zeros?
Okay, that's a zero matrix. Okay, but going back to an identity matrix, the main diagonal is all ones, everything else is 0. This is a very important matrix in the world of matrices because this is analogous to the number 1 in like for real numbers. Okay? The like an identity matrix is the same thing as the number 1. Okay? Okay, so let's talk about matrix operations. Adding and subtracting matrices is extremely simple. However, there is one condition. The matrices that you're adding and subtracting have to have identical dimensions. 3 by 4, 3 by 4. Otherwise, it doesn't work. Now, to add or subtract a matrix, it's so simple. It's like insulting your intelligence even. So look at this. This is the, position 1, 1. This is position 1, 1. You add them, and then you put it in that same position of the new matrix. Okay? So this is position, 2, 1. You add it to its corresponding position. You put it in there. And then subtracting is the same. So why don't we do one? Here we have A, B, and C matrices. I want to find A plus C, okay? I don't know, can you? They're not the same, so it's not possible. What are you right? Not possible. Okay, so B minus A, okay? B minus A. So here we go. This is B. I'm just going to rewrite them. It takes a couple of seconds to rewrite them, but it's so worth it because then you don't make a mistake. So B minus A. So here we go. This is a 2 by 2. This is a 2 by 2. My answer is going to be a 2 by 2. So basically, I take the first one and its corresponding one. 10 minus 2 is 8. It goes in the corresponding space. Okay? Next, negative 2 minus 5, negative 7. Negative 3 minus 1, negative 2. 16 minus 3, 13. That's it. That's how simple it is, adding and subtracting matrices. Okay, now multiplying is a whole other thing. We'll tackle that at another lesson. Scalar multiplication. Okay, so I keep saying in the world of matrices because the world of matrices is really a whole other realm in mathematics, right? So, there is, algebra, and then there is precalc, and then there is calculus, and then you've heard of linear algebra. Linear algebra is the world of matrices. It really is a world of its own. It's got its own rules. It's got its own everything, all right? In that world, you have matrices, which are numbers arranged in these arrays. And those are like the big guns, right? And then you've got regular old numbers, plain old whole numbers. Those are called the scalars. Scalars are all the numbers that until now you're used to dealing with. It's possible to multiply a matrix by a scalar number, okay, by a regular old number. The way in which you do that is, again, very, very simple. If you're multiplying negative 3 times this matrix, negative 3 is that scalar number. you literally just multiply it to every single number in there. So it'll be -3, -15, 0, 6, 18, -12. Okay, Sydney, did you have a question before? Yeah, you were raising your hand way before. Oh, okay. Okay. Questions? Okay, and then similar properties apply, like commutative property applies to matrices. So you can do A plus B or B plus A. Associative property, and then you can also distribute a scalar. So take a look at this. You have a matrix A, matrix B. Now you want to find 3 times A minus B. Just like with numbers, you could do 3 times matrix A, 3 times matrix B, and then subtract them. Or you could do A minus B, like Penn does, and then multiply by Q. So the same rules apply. Why don't we do it that way, actually, because it's a little bit more straightforward. So let's do 3 times A minus B. So this is 3 times A minus B. So we're going to do 5 minus 1, 4. Okay, since I'm keeping that order, A minus B, I'm okay with not writing it down. But if I was doing B minus A, I would probably rewrite them just so like I don't confuse things in my head, right? Okay, so -2 minus 0 is -2. -1 minus -2 is 1, right? 0 minus 3 is -3. 3 plus 1 is 4, and then -4. And then when I multiply in the 3, I get 12, -4, 3, -9, 12, -12. Oh yeah, -6, yeah. Okay? Yep. What do you mean by writing bracket? No, I didn't write it twice because this is 3 times all this. Yeah? Okay. Okay, so solving matrix equations. It's possible to have equations where the unknowns are matrices, not numbers. So for example, you know how when you have like 3x plus 2 equals 9, right? You solve this, right? You find x, and then all of these, the 3, the 2, the 9 are whole numbers. And when you solve it, x is also another whole number. You can have a similar situation, but all of the players are matrices. And when you solve, your x isn't a number, it's a matrix, okay? So for example, take a look here. You have A, matrix A, matrix B, and you have this equation, 2 times capital X minus capital A equals B. Each of these capital letters means it's a matrix, right? It stands for a matrix. So the way in which you do this is algebraically solve for x and then substitute the matrices in there. So here, if I have 2 times capital X minus A equals B, I want to solve for, yeah, what is X? It's 1/2 A plus B. Well, yeah, but it's like A and B are matrices, right? So now X, capital X, is going to be half of. It's up to you. We can add them in like this. So this is going to be A plus B, right? So -1 plus 5 is 4. 2, -2. 8 minus 4, 10. So finally, capital X is 2, 1, -1. Okay. It's up to you how many of those steps you want to skip. Remember, with each step that you skip, there's also less partial credit that could be given to you. So it's your call. Okay. Okay, so okay, in programming, they're used all over the place, right? To store information and so on. And then also, like, you know, if you have, let's say, I don't know, sales of like different products, right? You can arrange them that way by different years. And then if you want to do an operation, like what would happen if I like, you know, multiply all these by this, or right? It'll be easier for you to arrange and manipulate mathematically. Okay. All right, let's move on to 6.1. We're going to go back to solving linear systems, right? Remember when we had 3 equations and 3 unknowns, how we were solving them? We're going to solve those by matrices in this lesson, okay? Now, this process that we're going to be using is called Gaussian elimination. What is the process of Gaussian elimination? The process is if you have 3 equations and 3 unknowns, right? Here you had xyz, here you had xyz, here you had xyz. You eliminate half of the information here. So you end with xyz in the top, y and z in the second one, and just z in the third one. Okay? So you start off with 3 terms, 3 terms, 3 terms. You change it to 3 terms, 2 terms, 1 term. All right? That's the process. That process is called Gaussian elimination. In addition to that, the coefficients of the leading variables all have to be 1. Okay? You see that? So that's Gaussian elimination. Okay. So what happens with Gaussian elimination is you transform your equation into triangular form, or, new word, row echelon form. This is row echelon form. Okay? Now, what are some ways that you can do that? You are allowed to interchange any 2 equations. You're allowed to multiply one equation by another number. You're allowed to add multiples of equations together. Okay. The difference between this and what we've been doing before is you keep the unit intact, right? And then you just replace an equation with a new one. You never get rid of equations. So let's see. My go-to process, right, when I have an equation like this is I start with this one. I get rid of this one first. Then I get rid of this one. Then I get rid of this one. Okay, that's my go-to process. Okay, so bottom left first, then the upper one, then the one that says number 3. Okay, I've tried to lay it out here. Why don't we go step by step? We're going to solve this one. Okay. Okay, so the first one we're going to get rid of is this. Okay? But now, here's what we're going to do. Because that's my process, like that, I first get rid of that one, then the one above it, then the one to the right, and it's easy for me. So we're going to call this row 1, row 2, row 3. Okay. What we're going to do is, do you see this x? I need to get rid of this x. Okay? What can I do using just this column to get rid of? Okay, subtract 2 of them, right? Subtract 2 minus 3 or 3 minus 2. The difference, though, is the following. If this is the only one I'm changing, I have to rewrite the other 2 here. So 2x plus 2y plus 3z equals 6. Okay, so what I'm going to do here, and I always keep track of what I'm doing, I'm going to do row 2 minus row 3. When I do row 2 minus row 3, I do x minus x, I get 0. 2y minus y plus y. negative z minus z, negative 2z, equal to negative 3 minus 2, negative 5. Okay, do you see what happened? I found a way to make this 0. I did that operation and I just replaced it here. You are allowed to do that. You are allowed to replace a row with a combination of two other rows. Okay? Now, what's the next one I want to get rid of? This x right above it. Okay?
Not be able to do, like, what if we subtracted,
This one
yeah.
or this one?
No, the two eyes. Like,
Okay, but the thing is, I'm trying to make it into a triangular form. So I want to get rid of this, this, and this. I want to get rid of this triangle on the bottom. Okay? Okay, so here's what I'm going to do. Okay, so how can I get rid of that x? What do I do? Just look at this column. Yeah. Minus R1. Okay, so 2R2 minus R1. So look at this. This is going to stay unchanged now. So I copy it over. This is also going to stay unchanged, so I copy it over. The bottom one. Oh. Okay, here's what I said. I said we're going to do R2 minus, no. I said R1 minus 2R2. Or do you guys want to do the other way? Is that what we said? It doesn't matter. Okay, let's do that. Sorry. 2R2 minus R1. Okay? Yep. So 2R2 minus R1, that'll give me a 0. Now, you come over here. 2 times 2y minus this is 2y. Okay? What's the next one going to be? 2R2, negative 2z, minus 3z, negative 5z. 2 times negative 3, negative 6 minus 6, negative 12. Okay, basically here's where I'm at. Yeah, I want to make this into a 0. So look in that column. How do I combine with something in that column and make that a 0? Only by 2 times this minus this. Okay, now I'm here. The next one I need to get rid of is this y. Okay, so this is the next one I'm going to get rid of. Okay, so now look at what I have. I have empty here, empty there. Okay, why don't I get rid of these so you can see. Now, if I combine this third row with the first row, that won't work because I will be reintroducing an x term here. So the best thing to do is to combine the second row with the third row in the last step, right? So what are we going to do? R3 minus 2R2 minus 2R3. Okay, so what do you guys want to do? 2R3 minus R2. Oh. Okay, so whatever's not changing, I copy it down. Well, it would be 2y minus 2y. It would still be 0. It's okay because it'll be just the negative equation, which is fine. Still the bottom one, yeah. So 2R3, that's 2y, minus 2y is 0. 2R3, so that's negative 4z plus 5z. How much is that? Z. equals 2R3, that's negative 10, minus negative 12, so that's 2. If it confuses you, write it down. So 2 times negative 2z, minus negative 5z. Okay, if it confuses you, write it down on a scratch paper somewhere. So now, this is still not row echelon form because all of these have to be equal to 1. The coefficients here have to be equal to 1. So now what do? I do row 1 divided by 2. So I get x plus y plus 3 over 2z is equal to 3. I do row 2 divided by 2. Y minus 5 over 2z is equal to negative 12. And then this is the same. So this now is in row echelon form. Oh, yes. Okay. This is row echelon form. Okay? Now, can we use this to solve the equation? We can, because clearly z is equal to 2, right? So from row 3, z is equal to 2. Okay, now look. Now I'm going to use back substitution. Now I'm going to plug that into row 2, and then I'm going to use that. Okay, but work smart, not hard. I hate all these fractions, and you know what? I really don't want to work with all those fractions. So it's okay for me to go back and use this version. You see that? Huh? This one's easy, but if it was like a 5, then it wouldn't, right? So I'm saying you have the option of either using this one or this one. Okay, so from row 2, all right, let's keep with that last term then. Y minus 5 over 2 times 2 is equal to negative 6. Y minus 5 equals negative 6. Y equals minus 1. And then from row 1, x minus 1 plus 3 over 2 times 2 equals 3. So x minus 1 plus 3 equals 3. X equals 1. So the answer then is 1, negative 1, 2. That's how you need to give the answer. Okay, so what is the difference between what we did and what we've been doing? Is here, do you see how each row is replaced by a new row? You're not eliminating, you're just replacing. Okay, let's move on to matrices. How does, oh, yep. Okay. So do you notice the only thing we are working on are the coefficients, and then the x, y, z are just coming along for the ride every single time, and we just keep having to write x, y, z, x, y, z. So what if we could just get rid of, since it's only the coefficients we're working with, why don't we just get rid of the variables altogether and just work with the coefficients? That's where matrices come in. Yay! Okay, so you can do this whole thing but with matrices. So take a look. Here we have a system of equations. I can just take just the coefficients, since that's all I need, and put it into what I call an augmented matrix. Augmented means like separator, right? This is like, there's a line here. So basically the coefficients all go in here. The constants go in the last column. Okay? All right, and now I can do the process that I did before, the Gaussian elimination on this, but just matrices. So let's take a look at what row echelon means. Row echelon in a matrix means this main diagonal is all ones, everything underneath is zeros. All right, now sometimes it's possible that you get a full row of zeros. That also is row echelon form. So take a look at this first matrix here. Is that in row echelon form? Yes, right? What about the second one? No, because of this. However, to put it in row echelon form, you could swap the rows, right? Like you could just bring that to the bottom and then it would be. What about the last one? Is that in row echelon form? It is, yeah. Okay. Right. A row echelon. It's not in row echelon form because it's not like 1, 1, 1. Yeah. Okay. So let's solve this now using an augmented matrix. First, we're going to put this into a matrix form. Okay, I'm actually, instead of making you write this twice, hopefully you're using a pencil, but look at the first one. Do you see how you can divide everything here by a 5? Right? Why don't we do that? So you could also have done it in the matrix, but you could do it before. Why don't we do it here? I'm not going to make you guys rewrite this. So it'll be 1, -1, -1, 7. And then here, you can either do a solid line or a dashed line. I like to do a solid line because it's just easier. Okay, so now, again, I like to get rid of this one first. Now look, this isn't like the, the only way to do this. I just have found that it makes things easier because in the end, you only have like one option to deal with. Okay, so I'm going to keep these the same. Also, once we get a little bit more savvy with these, you don't have to restrict to one step each time. You can do multiple steps in one. Okay, so I'm going to get rid of that 3. What I do is this. I look at this column, the first column, and I ask myself, how can I combine the circled number with one of the ones on top in order to make the circled number 0? So what I would do here is I would do 3 row 2 plus row 3. Okay? 3 row 2 plus row 3. Is there a different combination? There is. Does it matter? Does not. So that's 0. Now look, again, if you're going to get confused, write it down on your scratch paper. So 3 row 2 plus row 3. You see that? I write it down. So -6 plus 2, -4. Okay? Huh? Okay, hang on. I'm one at a time. You can, no. Okay, if I'm changing row 3, I'm changing row 3. It doesn't matter what combination I'm doing. That's what I'm changing. So, okay, so yes, sorry. It was the other way around. So what was it? It was 3 row 2 plus row 3. So +4. So again, 3 row 2 plus row 3, right? How much would that be? -2? You see that? Okay. What do I get for the last term? -6. Good. Okay. So now, okay, look, at this step, you're more than welcome to divide this bottom by 2. Okay? So you have smaller numbers to deal with. So now, let's do both of those in one step. The next thing I'm going to get rid of is this. So let's go here. What is it? Row 1 plus row 2. Okay, the first row is going to stay unchanged, so I just copy that down. Now, row 1 plus row 2, I get a 0, 1, -4, -5, right? And then I'm also going to do row 3 divided by 2. Why? Because I can, and I get smaller numbers to deal with. Because who wants to deal with a 6 when you can deal with a 3 instead? So 0, 2, -1, -3. Okay. Next, what am I going to change? This 2. Okay, because remember, I want to get like 1, 1, 1 here. I want to get rid of these 3 at the bottom. So this 2 is what I'm going to get rid of. This is why I like to go in this order, because now both of these are zeros, so I can just use these 2 rows to get rid of it. If I use row 3 with row 1, it doesn't work because I reintroduce a number here. So for the last step, when you do this, just use the bottom 2 rows. So what are we going to do here? 2R2 minus R3. Okay, let's see. That's going to be 0, 0. So 2R2, -8, minus R3, -7. 2R2 is -10, plus 3. Oh my God, -7 again. Yes. Yeah. So here, this stays, these all just get copied over. Okay, so lastly, to put it in real row echelon form, I'm gonna divide the bottom row by -7, so I get 1, 1. Okay, so this is my matrix in row echelon form. Now, this first column is all the x's. The second column is all the y's. The last column is all the z's. The way I read this is if I'm going to read the first row, 1x minus 1y minus 1z is 7. No x's here. Y minus 4z equals -5. Do you see that? So what's the last row read? Row 3, z equals 1. So from row 2, that would be y minus 4z equals -5. Y minus 4 times 1 equals -5. Y is -1. And then row 1, x minus y minus z equals 7. X plus 1 minus 1 equals 7. So x is 7. So the answer is 7 minus 1, 1. Okay? How does that sound? Difficult? It's a lot, and it's a lot of getting used to. Now, on the homework, there is a couple that can be a little bit not lengthy, but like the numbers can get a little high and people get confused. So I have solutions to a couple of them that I've written them out that I'm just going to post on MyJack tonight so you can look at them as you're doing your homework. Okay? Madeline, then Todd. Yes. Then you would have to have that many rows. So you can have like 7 variables, but you need 7 rows. No. No, because, yeah. Okay, let's do special cases. Yes. Oh, wait, Todd, you had a question. Sorry. You first. Yes. Yeah, it'll be like 17 times 19 and then 19 times 17 or something. Yeah.
How do you get the 3R2?
So you have to look at what number you're getting rid of. So for example, here, I want to... Okay, you start with this number. Now I want to get rid of the 3. So you look at that column only. Huh? That's the easiest way to start, because you have to make this triangle into zeros. So you have to get rid of this one, this one, this one. Okay? So now to get rid of the 3, you have to combine it with that one. Let's do this next one, and so you'll see. So look at this. I have 1, 2, 1, 8, 2, 3, negative 1, 13. Okay, look, I need to get rid of this one first, okay? So, look at that one, and we have to combine it with another number in its column to get rid of it. Well, a really easy way to do that is R1 minus R3, right? Would that give you a 0 there? It would. So 2 minus 1 would be 1. 1 plus 2, 3, and then 3. Okay, look, in the same step, I'm going to do another one. You ready? So you don't have to keep writing the matrix over and over and over again. Which one is the next one we usually get rid of? The one right above, right? This one. So now, look in this column. If I want to get rid of the 2 using this column, what can I do? 2R1 minus R2. So let's do that. You can do that. 2R1 minus R2. 0. 4 minus 3, 1. 2R1 minus R2. That's 3. When I get tired, I start writing because my brain can't process too many things, right? So I start writing down my steps. So 16 minus 13, that's a 3. Oh boy, this doesn't change. No. Okay, wait, you're going to ruin my moment if it becomes negative 3, Olivia. Okay, so now, if I wanted to make this 0, right? If I want to make this one 0, and I subtract, what happens? I get a full row of zeros. Oh, no. But it's okay. Because if I get 0 equals 0, what does that mean? Infinitely many solutions. Right? So, when you're going to get infinitely many solutions, you can either stop here. When you get 2 identical rows, all 4 of them are identical, you can stop and you can say it's infinitely many solutions, or if you don't see it, you can stop there. But wait, we can't stop. Oh, okay, maybe we will stop there. Okay. Oh, I was just getting